Hi everyone. In this video we are going to discuss Taylor's theorem of a complex valued function. The function f of z is analytic in this disk mod z minus z naught less than r naught. So this is the interior part of a circle with center z naught and radius r naught. And if this function is analytic, then it has this power series representation summation n z minus z naught is to n, where n has this value. So this thing we have to prove. Okay, so let us start to discuss its proof. See, here we have a disk with center z naught, radius r naught, but initially we will consider a disk with center 0, origin, and radius r naught. So let us consider a function f of z is analytic inside mod z is equal to r naught. Getting? So see, here they have mentioned mod z minus z naught less than r naught. So that means interior part of a circle. So that's why we have clearly mentioned inside a circle. But see, here we have considered a circle with center origin. So let me show here. So we have a circle like this. We have a circle like this, okay, with center origin and radius r naught. So let me show here. So this is circle with radius r naught. Okay, so that function f of z is analytic inside this circle. Okay, so they have mentioned it is analytic inside the circle. They have not mentioned anything about outside and on boundary. So what we do, we will consider one more circle c naught. So let me write here, consider a circle c naught. That c naught is defined as mod z is equal to r naught, where r naught is less than capital R naught. Okay, so what I am doing, I am considering one more circle with center 0 0, origin, and radius small r naught. So we have a circle like this. So let me show here, its radius is small r naught. Okay, see, we have considered a circle smaller than the first one, so that's why the function will be analytic inside and on boundary also. Okay, so let me mention here. So therefore f is analytic inside and on c naught. So the function will be analytic inside and on also for a smaller circle, but for a larger circle it is simply analytic inside the circle. Getting? See, if the function is analytic inside and on boundary of a given curve C or C naught, then the Cauchy's integral formula is applicable. So that formula I am going to apply for this z. So I am considering one point z here. Let me show. Suppose we have point z here, which is at a distance r from the origin. Okay, I have shown in the diagram. So let me mention then for z such that mod z is equal to r, which is less than r naught, okay, by Cauchy's integral formula. So I am going to apply Cauchy's integral formula for that. So that formula says f of z is equal to 1 upon 2 pi I integration over c naught f of s upon s minus z ds. Okay, so that point I have chosen z, so that's why I have used the different variable s. So by Cauchy's integral formula we got this one. Okay, so now what we are going to do, we are going to solve this integration. Getting? We are going to solve the integration, but before that we need to do some calculations. So I am going to do that. We have some space, let us use, but see, that space is not enough, so make a screenshot of it, then we will go further. So now let us consider, okay, so I am going to consider 1 minus z raised to n upon 1 minus z. So we have to find its value. Okay, so let us see how to find its value. Basically 1 minus z raised to n upon 1 minus z is same as z raised to n minus 1 upon z minus 1. If you multiply numerator and denominator by minus 1, you will have this one. So let us divide. We are familiar with division of polynomials. So we are going to divide z raised to n minus 1 by z minus 1. So we want z raised to n, so that's why I will take here z raised to n minus 1. So if you take the product, z raised to n minus z raised to n minus 1. So let us subtract. So obviously sign will get changed here, okay, and these two terms will get cancelled. So z raised to n minus 1, I should copy or that carry that minus 1 there. After that we have to bring z raised to n minus 1. So that's why we should multiply it by z raised to n minus 2. Let us take product z raised to n minus 2 into z raised to n minus 1 and z raised to n minus 2 into minus 1 minus z raised to n minus 2. Let us subtract, sign will get changed. First two terms will get cancelled. This will be there, z raised to n minus 2. I should carry that minus 1 as it is. Again we have to do the same thing. So z raised to n minus 2 we have to bring, so I should multiply by z raised to n minus 3. Okay, so in this way we will continue. So did you notice one thing? The powers is reducing, powers are reducing, z raised to n minus 1, z raised to n minus 2, z raised to n minus 3 and so on. So it will be continued up to power 0. Z raised to 0 means 1. So that's why if you divide, we will have the polynomial like this, z raised to, let me write here, z raised to n minus 1 plus z raised to n minus 2 plus z raised to n minus 3 and so on, z plus z raised to 0, that means 1. Okay. After that what will I do? I will divide separately. So we will have 1 upon 1 minus z minus z raised to n upon 1 minus z. This will be as it is. So let us write it in a form of series. So we will have summation n running from 0 to n minus 1 z raised to n. The same thing I have written in a form of series. So let us shift this term to that side. So what will I get? So 1 upon 1 minus z is equal to summation n running from 0 to n minus 1 z raised to n plus z raised to n upon 1 minus z. Getting? So what we are doing this thing because to solve this integration, we are putting our efforts to solve this integration only, right? So 1 upon 1 minus z, we got its expansion. So let us talk about s minus z now. So therefore 1 upon s minus z. Shall I take s common? If I take s common, we will have s here 1 minus z by s. Okay. So yes, by taking s common we got this one. Let me write that 1 by s as it is. Let me remove this part. Okay, that was a rough work. So let me remove, so we will have some more space to write. See here 1 by s I have taken outside. Now we have 1 upon 1 minus z by s. Okay, we have a space, let us use. Okay, this space I am going to use for a further work. See, what will I get then? 1 by s, let me write. So this is equal to 1 by s. Let me write here 1 by s into 1 upon 1 minus z by s. See, 1 upon 1 minus z has an expansion, this one. So we can write in the same way. We can write the expansion of this one also. Simply at a place of z. At a place of z, we have to write z by s everywhere. Let us see what will I get. So we will have summation n running from 0 to n minus 1. At a place of z, we have to write z by s raised to n, getting, I am writing a bracket here, plus z by s raised to n divided by, here also 1 minus z by s. Okay, so let us do some work. 1 by s summation n running from 0 to n minus 1. We can take separate powers, right? So z raised to n upon s raised to n. Here we can cross multiply at a denominator. So z raised to n, here s raised to n. Here also we took separate powers and here we can cross multiply. So s minus z by s. Okay, so basically we have two terms here and we have 1 by s outside. So let us take product. Let us take 1 by s inside. So I am multiplying both terms to this by this 1 by s. So summation n 0 to n minus 1 z raised to n and s into s raised to n, s raised to n plus 1 plus z raised to n upon s raised to n. If you multiply this bracket to this 1 by, so s's cancel and s minus z. So finally, okay, finally we got the expansion of 1 upon s minus z. But see, here we have f of s also. So let us write f of s. Let us multiply both sides by f of s. So therefore, f of s upon s minus z is equal to summation n running from 0 to n minus 1 z raised to n f of s upon s raised to n plus 1, right, plus z raised to n f of s upon s raised to n s minus z. Okay, so we consider f of s also. So now we have to take integration. So let us integrate both sides. Okay, so what will I get? So therefore integration over c naught f of s ds upon s minus z, integration over c naught z raised, summation is also there. No, I should write summation n running from 0 to n minus 1 z raised to n f of s ds upon s raised to n plus 1. Here also we should integrate, integration over c naught z raised to n f of s upon s raised to n s minus z ds. So as I told you earlier, our target is to solve this integration. Okay, so we have reached up to the integration. See, simply 1 upon 2 pi is also there. So let us multiply both sides by 1 upon 2 pi. But see, there is no more space to write. Make a screenshot of it, then we will go further. So let us continue. See, purposely I have kept this equation 1. Okay, yes. So see, integration we have got. So simply we have to multiply both sides by 1 upon 2 pi. So let us do that. So therefore 1 upon 2 pi I integration over c naught f of s ds upon s minus z is equal to 1 upon 2 pi I, right? See, summation is there, okay, finite summation. So that's why we can easily interchange that summation and integration. So let me write that summation outside, n running from 0 to n minus 1 integration over c naught, right, z raised to n f of s upon s raised to n plus 1 ds plus, see, here we have an integration of s. So z raised to n, capital N, is independent on the summation. So let me take it outside. So it is constant, okay, since it is a function of z. So z raised to n integration over c naught, what we have, f of s upon s raised to n s minus z ds. Okay, but see, the left hand side is nothing but f of z. So from equation number 1 we can write the left hand side is nothing but our f of z. So let me directly write this is f of z is equal to 1 upon 2 pi I summation n running from 0 to n minus 1. You can easily see this is integration of s. So z raised to n is constant, for that we can take outside the integration z raised to n integration over c naught f of s divided by what we have, s raised to n plus 1. The same thing we can write in this way also, s minus 0 raised to n plus 1 ds. See, purposely I am writing in this way, okay, purposely. See, s minus 0 is again s, I know. So plus z raised to n integration over c naught f of s raised to n s minus z ds. I have written the same as it is, okay. So this is equal to 2 pi I summation n running from 0 to n minus 1 z raised to n, okay. See, are you familiar with extension of Cauchy's integral formula getting? So that formula I am going to use, extension of Cauchy's integral formula, since that bracket has power n plus 1. So that formula says, extension says, this is nothing but see, what will I have, 2 pi I by n factorial nth derivative of f at 0, since s minus 0 we have, and see, it has power n plus 1. So that's why we take nth derivative, and in denominator also we write n factorial. By extension of Cauchy's integral formula we got this one, plus let me copy as it is. So I'm writing copy paste. So 2 pi I and 2 pi I will get cancelled to each other. So finally what will we have, summation n running from 0 to n minus 1. So this is our f of z, let me write, and this is nth derivative of f at 0 upon n factorial. See, z raised to n is there, plus I should copy this part also, z raised to n. See, 1 upon 2 pi I, I should multiply here also. So this is 1 upon 2 pi I. On both sides we need to multiply. So 1 upon 2 pi will be there, right? Okay. So upon 2 pi I integration over C naught f of s upon s raised to n s minus z ds. So let me remove this part. So yes, this is very important thing we have got. Let me write here, let me remove this part. Okay, so now see, I will write the same thing. So therefore f of z is equal to summation n running from 0 to n minus 1 nth derivative of f of 0 upon n factorial z raised to n. See, I am calling it as rho n of z. I should mention what is our rho n of z. Rho n of z is z raised to n upon 2 pi I integration over C naught f of s upon s raised to n s minus z ds. So this is rho n of z. So now our target is to prove that rho n of z, we can call it as remainder also, it will converge to 0 as z tends to as n tends to infinity. So let me mention, now we will prove that that rho n of z, mod rho n of z will go to 0 as n tends to infinity. So this thing we are going to prove. Okay, see, we are going to use ML inequality for that. Just make a screenshot of it, then we will go further. So see, let us continue. See, as I told you earlier, we are going to use ML inequality to prove this mod goes to 0 as n tends to infinity. Getting? So before that, to actually applying ML inequality, we need to do some calculation. So let us do that calculation. Let us recall few things first. So we have, okay, at the beginning of this proof, we have already mentioned mod z is equal to, see, mod z is equal to r and mod s is equal to r naught. We have already mentioned. So let us consider this bracket s minus z. So then mod s minus z. So by inequality, we can write this is mod of mod s minus mod z. Mod s is equal to r naught minus mod z is equal to r, right? See, r naught is clearly greater than r, so obviously r naught minus r will be positive. So it is r naught minus r, right? So r naught minus r. So if, so let me mention here, therefore mod s minus z is greater than or equal to r naught minus r. But you can easily see that term is in denominator. So let us take reciprocal. So 1 upon mod s minus z is less than or equal to 1 upon r naught minus r. If you take reciprocal, inequality will get changed. See, let us consider s raised to n and 1 upon mod s raised to n. So you can take separate mod. So that's why mod s raised to n. If you have a multiplication, you can do this. Yes. So mod s is what? R naught. So this is equal to 1 upon r naught raised to n. So this thing we got. Let us consider one more thing. Okay. So you can easily see here, you can easily see integration we have, and inside the integration we have f of s, s raised to n and s minus z. So we have considered s raised to n and s minus z. So now it's time to consider f of s. So here I consider let capital M is equal to maximum value of f of s on C naught. So I will consider its maximum value. Okay. So all things are set now. So let me simply mention then mod f of s upon s raised to n s minus z. So I have considered all three terms simultaneously. Mod f of s has maximum value m, so we can mention less than or equal to m, right? S raised to n, its mod is r naught raised to n, and s minus z, its mod is less than or equal to r naught minus r. So all things we got here, right? So let us talk about length, and length of C naught, length of C naught. So that thing is also required for ML inequality. L means what? Length of a curve. So basically C naught is a circle, right, whose radius is R naught. So its length will be 2 pi R naught. Since we know length of a circle is nothing but its circumference, having formula 2 pi R. So that's why using that formula I got this one. So now it's time to consider its mod. Then mod Rnz. Okay, so this is equal to, so let us take its mod z raised to n upon 2 pi I integration over C naught f of s upon s raised to n s minus z ds. So here we can take separate mod. Okay, so we can take separate mod z raised to n mod 2 pi r. 2 pi I is also there, see, but mod of I is 1. So that's why I'm not writing it. I'm directly writing mod 2 pi, or simply you can write 2 pi also since it's positive real number. See, let me write it first 2 pi I, but mod of I is 1 into mod of this integration over C naught f of s upon s raised to n s minus z ds. Okay. So I want some space to write. So let me remove this part. So we will have some space to write. So therefore, let me write, therefore mod rho n of z, C is equal to mod z is equal to r. So r raised to n, 2 pi is positive real number, its mod will be as it is, I, its mod is 1. So for this integration I am going to use ML inequality. So its value will be less than or equal to m into L. Our m is this part into, let me write, m upon r naught raised to n, r naught minus r into L means length, 2 pi r naught. So tell me what can we cancel here? Definitely we can cancel 2 pi. So we will have r raised to n, m, and r naught also, right? And yes, 2 pi r naught and r naught raised to n and r naught minus r. So what will I do? See, r raised to n and r naught raised to n. So let us write a common power n. So m r naught upon r naught minus r and r upon r naught raised to n. Okay. So there is no more space to write. Make a screenshot of it, then we will go further. So let me conclude here. So therefore mod rho n of z, what we have got, less than or equal to m r naught upon r naught minus r, right, r upon r naught raised to n. But see, basically that r is less than r naught. See, r is less than r naught, so therefore r upon r naught is less than 1. Getting? So if you have any number less than 1 and if you take its higher power, then it will go to 0. So therefore r upon r naught raised to n will go to 0 as our n tends to infinity. See, let me mention here. Yes. See, this number goes to 0. That means 0 into anything 0. So mod of rho n of z is less than or equal to 0. But actually there is a mod. So it cannot be negative. So that is also greater than or equal to 0. That means our conclusion is, therefore mod rho n of z tends to 0 as n tends to infinity. Getting? As n going to infinity, its value will be 0. So then equation 2 becomes. Then 2 becomes our 2 will be f of z is equal to summation n running from 0 to n minus 1 we had written, but see, our n is going to infinity. So I should mention infinity here. You can go back in this video and check the equation number 2, so you can easily understand what I am writing there. Nth derivative of f at 0 upon n factorial z raised to n for mod z less than or equal to r naught. But see, that small r naught is less than capital R naught. So therefore we can write f of z is equal to summation n running from 0 to infinity, nth derivative of 0 upon n factorial z raised to n for mod z less than capital R naught. Getting? It is true. This series is true for mod z less than or equal to r naught, but see r naught is less than capital R naught, so that's why it is true for capital R naught also. See, I want some more space to write, make a screenshot, then I will go further. See here, actually let me mention here f of z is analytic. See, initially they have mentioned analytic, so let me call it as 3. So f of z is analytic, so that's why f of z plus z naught is also analytic. That means if you simply add a constant, complex constant, then also it is analytic. So it implies we can write g of z, which is defined in this way by simply adding z naught to z, is also analytic. So if it is also analytic, then we can write the same expansion for that g also. Then from 2, let me write, then from 2 we can write g of z is equal to summation. This is also analytic function, no? So we can write expansion for that g also, 0 upon n factorial z raised to n, let me mention, for mod z less than r naught. So now let us substitute the value of g. What is the value of g? This one let me write here. Therefore, f of z plus z naught is equal to summation n running from 0 to infinity, nth derivative of g at 0. That means here at a place of z we have to put 0. If I put 0 here, f of z naught we will have. So nth derivative of f of z naught upon n factorial z raised to n for mod z less than r naught. Now what I am going to do, I am going to replace z by z minus z naught. Now replacing z by z minus z naught everywhere. Let us see what will happen. Therefore f of, here also I am putting I am replacing z by z minus z naught. So z naught and minus z naught will get cancelled, and we will have f of z summation n running from 0 to infinity, nth derivative of f of z naught upon n factorial. Here also we should replace z by what? Z minus z naught raised to n, for here also we should replace z by z minus z naught. So mod z minus z naught less than r naught. So in this way we proved if you have an analytic function f of z in a disk mod z minus z naught less than r naught, then it will have the power series representation in this way. Okay, so if you call it as n, the series will look like this: summation n running from 0 to infinity, I am calling it as n, okay, z minus z naught raised to n for mod z minus z naught less than r naught, where I should mention what is our n. Our n is nothing but this nth derivative of f at z naught upon n. So in this way we proved Taylor's theorem. Make a screenshot of it, then we will stop. Thank you. See you.